Hello everyone, in this video I'm going to walk you through these questions. So this question is SQ4 of our special antenna exercise. You are given an vertical electrically small magnetic dipole. So when you say magnetic dipole, this means it's a coil, it's uh, a current ring, current loop. Is an infinitesimal vertical magnetic dipole. This means it is electrically small. Equatorial current IM. Let me and it is mounted at the height of h about the infinite perfectly conducting electric ground planes. Part A. Determine the far field component radiated by the dipole in the presence of the ground planes. Part B. Specify the angular regions where the radiation fields are valid. So the radiation field should be about the ground. Yeah? So part B is nothing difficult. Okay, I'm going to start now. Okay. So first of all, in this question, SQ3, SQ4, you have a dipole antenna. Magnetic dipole. Magnetic dipole, as I told you, is a electrically small wire loop. So V, Y, X. Because you have a infinitesimal ground planes. Sorry, because you have a perfect ground planes on the XY plane, so you will form an image here. So this is a image antenna, and this is blue. This is a physical antenna. The height here is h. So obviously, in the image, you also get the height h here. Now, before moving forward, we need to determine the polarity of the dipole. So suppose you have a current, yeah, your magnetic field is pointing upward. Let me see if I have any different colors. And I want to use different colors. So, okay, we have. So suppose the dipole is pointing upward in the upward direction. This means the current is going, yeah, you use right hand screw rule. Yeah, if the magnetic field is pointing upward, the north is up, then the current should be anti-clockwise. And the tangential electric field on the conducting plane has to be zero. So you might end up with a electric field on the ground like this. Yeah, because of the current here, you will produce a electric field in the same direction. But the tangential electric field has to be zero. So this means you have a image electric field in the backward direction. So the blue circle is in the clockwise, anti-clockwise direction. Then the red circle is in the clockwise direction. This is the only way to balance out the uh, tangential electric field. So now the in terms of the current, the current in the image antenna will be moving um, backward. So backward. So like this. So this is the right way to absorb the. So in other words, if you have a electric field here, E, uh, then the electric field in the image will be negative E. Uh, so this is the way how we determine the sign. So if I am going to draw the arrow, this should be pointing downward, and this will be pointing downward. When you use the right hand screw rule, it's pointing downward, and for this one, it's pointing upward. Okay, so now let's move on. Uh, make sure you don't get the direction wrong. So now the electric field as given by the question, the E theta is equals to K I naught and then L and then 4 pi and then E J K R divided by R and then sine theta. And this is the electric field in the direction of theta. And what you need now is to use duality theorem to convert this electric field into magnetic field. So you replace E with H. And for every theta, you make an inverse. K will not be changed. I naught will be converted to Im, where Im is the magnetic current. It doesn't exist in nature. There is no such thing as magnetic current, but we just assume one here. L is the length. Don't need to care about this. 4 pi is still 4 pi. And now the phase and the denominator will remain the same. Okay? Other thing is just like the constant. Now it's you like this. So now what you need to do is to convert this equation into maximum electric field as the question given. As the question given, uh, E is equals to similarly. I can also say this E phi can be written as H theta, where the angle in this case is theta. Sorry, phi, yeah. So using this concept, right, we can rewrite the circular electric E V. By the way, I think there is a minus sign here because you convert the electric field into an. So there should be a minus sign. Is that right? Okay, I will just write it down. I will just assume it is. So this guy times this guy. So the theta what cancel out. Then this term will remain the same. This term has nothing to do with the quantity. Sorry, this one. Okay. So the first part of the question, determine the far field component radiating by the dipole in the presence of the ground plane. Yeah, I'm going to do it now. Now, first of all, if you consider the far field, then you know the upper magnetic dipole will radiate out. This is the direction of propagation, and the bottom one will be the same. So arrow here. So I will assume the field component originated from the view antenna is arrow of 1. So this is arrow of 1. And in terms of distance, arrow of 1. The view component, as a result of the image antenna, will go through this pathway. This pathway is arrow of 2. And the combined pathway is arrow. Yeah. So you need to find the phase difference. At far field, the magnitude, in terms of magnitude, arrow of 1 and arrow of 2 and arrow should be the same. But in terms of the phase, we have to be careful. The phase here is the height is 6, right? So the length here, the phase here, yeah, I will do it like this, H cosine theta. Yeah, it's very messy. But I can improve. Yeah, I can improve. Yeah, I don't want you to get confused. Okay, so I will just write it down like this. So now what we have here is R1 is equals to this minus the phase shift. The H cosine theta. And the bottom one is R2, it is R plus H cosine theta. So this is how we determine the phase shift of this value here is H cosine theta. And similarly, if you draw a perpendicular projection onto R2, this ratio here is h cosine theta, and R2 is equal to this one plus this ratio. For the upper one is R1 minus ratio, the ratio, right? So never get confused. So now the total electric field is E of T is equal to E phi 1 plus E phi 2. This means the electric field going through this pathway and the electric field going through this pathway. Now, at the observation point, this is how we calculate the combined electric field. And we are going to use this equation. We add it up. So we add this up, and J, K, I, M, L, and then 4 pi. And then I'm going to write down this term first. And we know the angle, yeah, the direction, yeah. And then this one here will be E, J, K, R1, then R1. And then the second term, right, you have to be careful because the upper term is in the anti-clockwise direction, but the lower term, the magnetic, the current in the loop is in the clockwise direction, so it's opposite. So you need to use minus here. Arrow 2 and then arrow 2. So this is how we get it done. We don't need this. Okay. Now, for magnitude, you can have soon arrow 1 for phase, right? So for phase, we have these two equations. For phase, we can have this. But for magnitude, we have arrow 1, arrow 2, and arrow. They are more or less the same. So we are going to use these two assumptions to approximate the far field. So E of T, which is the array vector, formed by the real antenna and the image antenna. And then we write down the constant in the coefficient, then 4 pi and sine theta. And then we take out R here because we are in terms of magnitude, right? R1 and R2 are similar. But the phase, you cannot use this assumption to approximate the phase. You have to calculate it accurately. The phase can be a huge issue. So E K R1 according to here is minus H cosine theta. And then minus E J K R plus H cosine theta. So it's very cloud. So this is the what we have got. I am going to write down more clear. It's not clear. It's too cloudy. So I hope this is much clearer now. Now, both terms have okay, jk. Yeah, sorry. So now both terms have a common factor, e to the minus jkr. Yeah, so we can take it out. And 1 over r. And remember, uh, I have just said that the both terms have e minus 3 to the power 3, minus 3kr and divided by r. So they are both common. And now this is very clear now. E and then j k h cosine theta and then minus e minus j k h cosine theta. So I think you would agree this one will end up to be a sine term. So I am running out of space, but I can erase the upper part here to continue with our solution. So am I will continue here. So E of t is equals to j k I m l o and then 4 pi. And yeah, not very clear. Pen is not very important. Let me change to another pen. This one is even worse. And then j k I m l o and then 4 pi and then sine theta and then and uh, and then here is 2j sine k cosine theta. So I hope this is clear enough. Now it's quite clear. You can I think to some extent at the time when I convert I might have missed the minus sign, I believe. So there is a minus sign here. So I will do this here. Yeah, I will do it here. At the time when I convert from magnetic to electric, then I missed the minus sign. So these two can cancel out, and j minus j is minus one and minus here because you delete the minus sign. So 2 pi then sine. So this is my solution. And this solution, in my understanding, by the way, we also need to make sure you don't get the angle wrong. It's a circular electric field. And for magnetic field, you just need to uh, use the equation, right? H theta is equal to minus E t divided by, sorry, multiply, divided by this. And then the angle here So this means um, E, sorry, extra is equal to A I M L 2 pi delta I delta that n times. Don't forget that this is okay. The in terms of the magnetic field, so this is the answer for the first part. Wonder whether there's any second part. So specify the angular region where the radiated fields are valid. I'm going to show you because in this case only the field above the ground planes exist. Below the ground plane there shouldn't be any electric field. So in this case you might have shown the in terms of the angle. Yeah, theta should be below the second part, uh, below pi over 2 and minus pi over 2. So this is my second part. Yeah, because you can still hear like this, like this. Below the infinity infinite ground plane, there will be no yet. So this is the suggestion. Okay, if you have any further question, please leave your question to the comment section. Thank you for your help. Thank you. Bye bye.